Okay, guys, welcome back. Today's day 6 of rotational dynamics, and in yesterday's class, I've discussed a lot about moment of inertia of different bodies. But at the end of the class, I asked you to remember all the values. And yeah, it is good to remember the derivations of all these bodies. It's a good thing, but the derivations take too much of time to explain in the class, so I'm not doing it. They're available in the textbook. And again, strictly speaking, it's the values that are really important, the end values that are really important for all the kind of bodies. What are the bodies that you face? We are going to face mostly disk, sphere, hollow sphere, solid sphere kind of things. Like, we're not going to face some random strange bodies. Okay, most of the situation will be facing a disk in a very or a ring. Disk or a ring are the like most frequent bodies. You'll be getting a hollow sphere and a solid sphere sometimes, so you don't really have to worry about that part. And I hope you remember the values. If you don't, please go ahead and remember. And at the end of the class yesterday, I talked about parallel axis and perpendicular axis theorem. I asked you to go through H.C. Verma's textbook, but yet anyway, I said I'll discuss these things. Like, I'll just remind you the idea about it. If only you know the moment of inertia about center of mass for a body, if only you know the value of this thing already, and you want some random point which is at a distance d, and you want the moment of inertia about this axis, the new axis, the moment of inertia is simply old plus that additional md square value. That's all. Okay, that is the parallel axis theorem. And in perpendicular axis theorem, all we had is Iz is nothing but summation of Ix plus Iy. Like, you have a disk. This is the Iz, this is Ix, and this is Iy. So the summation of these two axes is simply gives you the moment of inertia about this axis. And I already mentioned that it used this own idea only in 2D. We can use this in 3D sometimes, but it's not advisable. I mean, you need to clearly understand where you're doing that. So just completely stick to 2D bodies. Don't use this perpendicular axis theorem anywhere. Now, anyway, I wanted to discuss this, like how these things actually arrive. Like, how did we arrive at this idea? I wanted to discuss that. So let me just start with that idea and show you some moment of inertia, some examples, and let's see how far we can go today. Okay, so you have any random body about the axis. So this is the center of mass. So ICOM, let's just write it as. Now you're taking some other axis. We don't know what this is. So let's just call it as I1. And the distance between them is d. So I can clearly write, like I mentioned yesterday, I center of mass plus md square. But how are we doing this? How did we approach at this problem? So how are we supposed to determine for 3D axis and perpendicular axis theorem? No, you don't need that. Sharath is asking about how we supposed to do in 3D bodies. You don't need that. You'll understand. Like, let's just go slowly and you'll clearly understand. Okay. So how do we get this thing? Like, how do we approach this problem? So to explain this, I'm going to give you the same explanation that is there in H.C. Verma. This is nothing new. Wait a second. I think I've built a model for this also. Let's just see. I'll try to explain it here as much as possible, and then we go into the model. Let us call this as a center of mass axis. So we already know this value, I center of mass, and you moving away from the center of mass by a distance d. Okay. Now I'm not considering the entire body. I'm considering this specific particle whose mass is very small, which is m. Let us just call it as m, and this distance is r. This distance is r. So the particle's moment of inertia is basically mr square. Now I'm not talking about the entire body, guys. Clearly, this is not a 3D body. This is a 2D body. Let me just take you to the model itself. It's better that way. I don't want any confusions to you people. Look at this situation, guys. Let us just take a disk. Let us just take a disk only. And about the axis that we are all looking at, about this axis, everyone knows the moment of inertia for disk is mr square by 2. Okay. I've taken a disk. We can take any random body, but I cannot draw any random shape on this app. So I'm just taking a disk. We can take any body randomly. And let us just call this as the value as icom. Okay. Now, what I'm trying to do here is, let me just delete this thing. We don't need any confusions. So what I'm trying to do is, we already know the center of mass, about center of mass. I'm considering a small particle whose mass is m, which is at a distance r. So the moment of inertia of that particle, only just that particle, is basically mr square. Okay, now I'm going to take another axis which is parallel to this axis. Let me show that to you in the so that make more sense to you people. Like, yeah, you see the black axis. Okay, so what I'm trying to say is, let me not. No, let's take a big screenshot. So what I'm trying to say is, this is r and the distance between the axis is d. We already know the moment of inertia about this thing is as I center of mass. Let it be like that. We don't need that for a while. So the moment of inertia of only this particle is basically mr square. But I want the moment of inertia about this axis of the same particle. Let us just say this is the distance now. Let me take it to you from the top view so that it makes sense to you people. So I'm taking the top view. Oh, if I'm taking the top view, I can't see the axis. Just let's just say it is somewhere in between 2 and 4, right? Yeah. Let's just take the point as 3 itself. Okay. I'm taking a screenshot now. So this distance is r. This is where the axis is. I hope you clearly understand. Oh, I'm sorry about it. I hope you clearly understand that we are looking at the top view. Let me show that to you anyway. Again, we are looking at the top view. You're looking at both the axis, and I'm going to the top view. This is the distance that we already know, and this is where the another axis is, and we don't know this distance, but we know this distance. Okay, now what we're going to do is, let's just do some basic geometry problems. Okay, let's just name all of them. This is named as D already. Let's just name it as A. Let us name it as P. Let me delete this bit. AD square is the distance that we need, right? Because the moment of inertia about this axis depends on this distance only, right? So m into AD square, that is what we need. Now I'm going to write AD square as, I'm going to take this triangle. I'm going to delete it anyway. Again, let us take another point which is called as C. From the right angle triangle ACD, can I write AD square? Can I write AD square equals to AC square plus CD square? Can we do that? Now, AC square plus CD square. Now, we clearly need this value AD square. AD is the distance which is from the of the point from the new axis. That is what we need. Now I'm taking AD. Now AC is clearly summation of AP plus PC. Do you agree? AP plus PC. If only I expand it, AD square equals to AP square plus PC square plus, I'm writing it here, and the left out term, which is nothing but 2AP PC. A square plus B square plus 2AB. I wrote the last word away. There's a reason why. Now, if I clearly look at these two terms, PC square plus CD square, which is nothing but PC square plus CD square, it's nothing but PD square. Do you agree? So I'm going to write the rest of the part here. Clearly watch, guys. AD square equals to AP square AP square is here, and this part, this whole thing is directly written as PD square plus 2AP PC. 2AP PC. Okay. You're clear until now, right? Like already it is basic geometry only. Now, if I multiply m with all of these things, I'm just be simply multiplying this thing. So m into AD square is the moment of inertia about the new axis. So I new. M into AP square is nothing but AP is nothing but D, so which is nothing but MD square. This is nothing but I center of mass. So I nu equals to MD square plus I center of mass, and there is this additional term. This is where all the trick is, guys. This is where all this trick is. If only I clearly look at it, it is M into PC. Let's just ignore this AP value. This is a constant. Let's just ignore this value. M into PC. Now PC is nothing but if only I have to write the coordinates of this thing, x comma y. PC is nothing but x. So you're writing M into x coordinate. And if only I write the summation, until now there is no problem. If only I write the summation, I'm writing in summation of mx. Summation of mx is basically the location of center of mass. The summation of mx is nothing but the location of center of mass. Obviously, there is a capital M, like total summation is there. But summation of center of mass, sorry, summation of mx is nothing but location of center of mass. Now, what is the location of center of mass from center of mass? Because we are only taking P as the origin, and we're trying to find the location of center of mass. We are trying to find the location of P from P. So this value right here simply becomes 0. So this entire value simply becomes 0. And this is what you're left with. I nu equals to md square plus I center of mass. Guys, I know it is a bit confusing. I suggest you to look at what is there in HC Verma now. It makes more sense now for sure. Or after the class, I suggest you to watch this video again slowly. I assure you that you will definitely get it. But even if you don't get it, it's not that of a big deal again. Like nobody is going to ask you why you got it. This is basically like a IP question. So theoretically speaking, so nobody is going to ask you about why you got it and all. Everybody is going to stick to the point saying whenever you're moving away from the center of mass by a distance d, you always simply write I center of mass plus md square. I center of mass plus md square. That's all. Let us just use this idea a bit somewhere. Okay. Let us just use it for a disk only. Okay. I have a disk. About this disk, everyone knows the moment of inertia about this thing is mr square by 2. I want the moment of inertia about this axis, which is at the edge. So I'm not talking about disk rotating about its center. I'm talking about disk rotating like this. Like if the disk is like this, it is rotating about its edge. Okay. So if only you want this, everyone knows the distance is r. So mr square by 2 plus md square. Md square, the d is here is nothing but r. So the value will be 3 by 2 mr square. So the moment of inertia about a disk of a disk by its edge like this is simply mr square by 2. Okay, I hope you get it. I'll discuss more ideas here. Take a rod, a basic rod. Everyone knows this value. About center, it was ml square by 12, right? Everyone remembers this value. About center for a rod, basic rod, about center, if it is rotating, ml square by 12. And I want to shift it by a distance d. Even though we know the answer, the d is nothing but L by 2 here. Like I want to go to the edge. Even though I know the answer, I'm just checking it. So the moment of inertia about this axis will be ml square by 12 plus md square, m into d square. D is nothing but ml by 2 whole square. If I write the summation ml square by 12 plus ml square by 4, you clearly get the value as ml square by 3. If you're good at calculation, you make a quick calculation, you will actually get the value that we already know, ml square by 3. Okay, it comes in handy when you want to find it about this axis or this axis or this axis or this axis. Now make sure you're always going from the center of mass only. You can't take a random body like let us say you have a disk. Let us say you already know this value. Somebody gave this value I1 and I want the value of I2. You cannot say I2 equals to I1 plus this, let us just call it as this distance is as some smaller. If only you write this is a big blunder. You cannot do that. It is always from the center of mass. The distance, the axis shifting must always happen from center of mass. Now, if only you have to do it, somebody actually gave you, sorry about it. Somebody actually gave you a problem saying he gave you this value and he's asking this value, let us say. First shift it to center of mass by writing minus md square. Like let us write this distance is d1 and this is where the center of mass. So first subtract it, go to center of mass by decreasing the value. From that center of mass again go back. This value, this idea is always valid only from when you're going from center of mass, not anywhere else. Guys, if it is too much for you, it's totally fine. All you need to do is like basic understanding of basic remembrance of all these values. Okay. Aniket, what is it?
Sir, it applies to 3D bodies also.
Yes, this thing definitely applies to a 3D body. Like let us say you have a cylinder. You have a cylinder, and moment of inertia of cylinder is mr square by 2, and about this axis you want mr square by 2 plus md square, which is nothing but mr square. So for a cylinder, about its edge, the moment of inertia is clearly uh, what 3 by 2 mr square. Yes. For a sphere, like let us talk about a hollow sphere and a solid sphere also. Let us take a hollow sphere first of all. Whenever I'm drawing this thing, just imagine this is a hollow sphere. Okay, we already know this value as 2 by 3 mr square. All you need to do is like if somebody asks you about this axis, all you have to do is you simply write 2 by 3 mr square plus md square. The d is here is nothing but r, so this value. Okay, so it is simple. If you want for a solid sphere, let us just say you for a solid sphere, what's the value? It is 2 by 5 mr square. Yeah, this is 2 by 3, this is 2 by 5. So for a solid sphere about this axis, 2 by 5 mr square plus md square. Md is nothing but r here, so mr square. That's all. Can somebody give me the answer for this? What do we have here? We have a ring. For a ring, everyone knows about this axis, which is nothing but mr square. I want about this axis. Can somebody immediately give me the answer? What is the moment of inertia about of the ring about that specific axis? Okay, Aniket.
Sir, 2 mr square.
Exactly. So the distance here is r again. So okay, everyone immediately like, oh, you all took time to type it. Fine. So md square is nothing but mr square. Uh, Let us look at more bodies now. No, no. Let's
It
just take
applies
some
to all
time.
bodies.
What?
This thing applies to all bodies.
Yeah, this parallel axis theorem, sorry, parallel axis theorem applies to all bodies. You must move away from the center of mass. One of the axes must be about center of mass for sure. Okay. So about center of mass, it definitely applies to all the bodies. Like, yeah, even for a human body, it applies definitely. Okay. So that's not a problem, just from the center of mass. Okay. Now let us look at the parallel axis theorem. Sorry, perpendicular axis theorem. In a perpendicular axis theorem, let's just go back here and forget about the black axis. Let's remove that. In the perpendicular axis theorem, understanding a perpendicular axis theorem is very simple compared to that thing. Okay, like you don't even have to put any time here. All you need to do is like clearly observe this thing. Let me take a screenshot of this. Let us call this as z axis, this as x axis, and this as y axis. Okay, I want the moment of inertia. We already know the moment of inertia about this thing. This distance, let us call it as z only. Okay, now this distance is called as y. This distance is called as x. Let's just say them like the values. Let's just name it like that. They're not really that values. Now, if only you want the moment of inertia, I z of that specific particle is nothing but small mass into z square. Ix is nothing but mx square, right? Because the perpendicular distance is only x. Now Iy is nothing but my square. But you can clearly see one thing, that this is a right angle triangle and x square plus y square equals to z square. So as long as you have this, you multiply m, this is nothing but ix plus iy, which is equals to iz. And that is a simple basic theorem everyone can apply, which is where you simply can apply anywhere. Like for a 2D body, you do not apply this for a 3D body. You are going to hell if you do that. Okay, don't do that, because I'll just give you an example. Okay, the best example that we can come across for a 3D body, it fails. For a 3D body, as long as it's for a 2D body, guys, you can go ahead and use this thing. Iy, let's call this as Ix and Iz. So Iz equals to Ix plus Iy. You can definitely use this thing, no problem at all. But the best example where it fails, Aditya already gave the answer. A sphere. You take a sphere, it doesn't really matter in a sphere where you're talking about Ix or Iy or Iz. All the axes are basically diameters only. So if you write Ix plus Iy, which is equals to 1 plus 1, you're basically writing 1 plus 1 equals to 1. It's not true, right? So basically, for a sphere, Ix is, let's take this as a solid sphere, 2 by 5 mr square here. This is also 2 by 5 mr square. And this is also 2 by 5 mr square. Okay, so you don't have to change the value. You shouldn't change the value. Like you shouldn't use the idea of perpendicular axis theorem in the situation of a, what do you say, a 3D body, not just a sphere, a 3D body in fact. Okay, you can't use that. Like somebody is trying to use, let us say, you know this value already, know this value as mr square. If only you use this idea for Ix and Iy, you are making a big blunder. A lot of people tend to make a mistake. They use the idea in cylinder also. You can use it in disk. There's nothing wrong in that. But you cannot use this idea for a cylinder, okay? Because Ix and Iy values are very difficult to find when it comes to a cylinder. We will get to see some problems where you have to find Ix and Iy for a cylinder. We'll do that, but you only know the value of Iz for a cylinder, not Ix and Iy. Okay, you cannot use this thing. We need 4D axis. What cone also is a 3D body. You cannot use the same idea for cone also. Just don't use it for a 3D body. What are the uses in 2D bodies? I'll show you. Like we have plenty of uses in 2D bodies. Let's just take one by one example. Okay, like let us start with a ring. Let us start with a basic example, which is a ring, which is mr square. Now this axis and this axis, Ix and Iy, clearly they're equal, right? For a ring, it doesn't really matter about x-axis and y-axis. So hollow cone, Aditya is asking about hollow cone. Even for a hollow cone is also a 3D body. Hollow cone is not a 2D body, you stupid. So Ix plus Iy equals to Iz. Iz is clearly here is mr square. And everyone knows Ix and Iy equal. So I'm writing 2Ix or 2Iy, it's fine. So Ix equals to mr square by 2. Don't get confused by these values. So for a ring, about this axis, moment of inertia is mr square. About this axis, it is mr square by 2. Or about any diameter, like for a ring, you take, for a ring, about any axis, you take, the moment of inertia is always mr square by 2. Okay, so it doesn't really matter. Mr square by 2, you remember this idea, okay? It's an important idea. Let us talk about the next body, which is, let's talk about a disk, shall we? We already talked about a disk, I guess, right? Disk, how do I do it? What's the best example that I can come up? Now the basic example only. Mr square by 2, Ix and Iy. So Ix plus Iy equals to mr square by 2 this time. So 2Ix equals to this value. So Ix simply becomes mr square by 4. The moment of inertia is mr square by 4 along the diameter for a disk. Okay, now you can apply the parallel axis theorem again, guys. Like I want to look at this thing. I want you people to look at this thing. We've just tried this axis, right? We've just tried this axis, which is nothing but mr square by 2. What about a axis like this, parallel to this thing? I'll try to show it to you on the thing. It is much easier. Let us just consider the disk only. Let me delete this thing. I'm writing the examples. This about this thing, it is disk. It is a disk. So mr square by 2. I'm starting with mr square by 2. So about this axis and about this axis, it is mr square by 4 and mr square by 4. Now, if I have an axis parallel to z axis like this, like vertically standing, Okay, I'll put it there, and you give me the answer about that axis. Uh, how do I put it? A parallel line. A parallel line, yes. Yeah. So let's look at this line. Oh, yeah, let us look at this line. If in this case, obviously the moment of inertia is something that we've already done. So about this axis, it is mr square by 2. We've known that the distance is r, so it is nothing but mr square by 2 plus mr square. So that's an easy value. Machan Avyasri, your camera is switched on, please. Now, I want the moment of inertia about this axis. Let me show it to you. Yeah, that's way too far. Let me put it properly. Mm, no, no, no. Parallel line. No, come on. I want a parallel line to this. Array. It's not happening, guys. Let me just draw it clearly to you people. So about this axis, we know the value is mr square by 4. Mr square by 4. I want about this axis. So it is about the distance adding only. So mr square by 4 plus md square, which is nothing but again mr square. That distance is nothing but r, right? So I put it there. I get 5 by 4 mr square. Yes. So for a disk also, you should know all these values. Like you remember the basic value and rest of the values all pile up together. So you don't really have to worry about the rest of the values. Okay. Important thing is important bodies are coming to the next idea is a square plate. A square plate is something which is interesting. Okay. Square plate. How are you going to find the moment of inertia of a square plate? A squarish plate. Can somebody give me an idea? We have a lot of versions to it. Aditya already raised his hand. Aditya, how
Cut
can
out
you do that?
small rods, sir.
Yeah,
Cut out small rods. Rod.
yeah. A small rod is it's basically a small rod which is extended, right? We've already
Yes.
done for this thing.
Anywhere
Like,
from
let me show
minus
that
a
to
by
you.
2 to a by 2, sir.
No, 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 no. Watch this thing clearly. This is interesting. For a square plate, about this axis we've already done, which is nothing but which only depends on this distance. I've already talked about it. Doesn't depend on this distance. It only depends on this distance. Any distance is a basically. So the moment of inertia about this thing is ma square by 3. The moment of inertia about this axis for a square plate is ma square by 3. I move parallel to the center of mass. I moved towards the center of mass. So I have to subtract the value. The distance is d. So I write ma square by 3 minus md square. That how much is d here? Ma square by 3 minus m into d value is
By
a
2,
by
sir.
2 here, right? So I put a by 2. So I have ma square by 3 minus ma square by
So we'll
4.
get ms square upon 12, sir.
Ma square by 12. Guys, so understand, I'm drawing the 3D body now. I'm not 3D body, I mean like a 3D vision, let's just say. So this is a square plate. We started with this axis. We started with this axis. About that axis, we got it as ma square by 3. I did a parallel axis theorem finding this value as ma square by 12. Is that what we got? It is nothing but, yeah, ma square by 12.
Sir, I tried directly with com only and I got the same value, sir.
Okay, okay. So if you have this value, let me delete this thing. We don't need this value anymore. If you have this as ma square by 12, we are pretty sure. Oh, whoa, whoa, okay. We are pretty sure that this value is also ma square by 12 because it's a squarish plate. Now that you have both ma square by 12, can somebody give me the value of moment of inertia about this axis? Aditya, you have muted yourself. What is the moment of inertia about this axis now?
ma square upon 6, sir.
Exactly, ma square by 6, because you simply add iy
Perpendicular
to
axis theorem, sir.
ix. You're using perpendicular axis theorem. Ix plus iy equals to ma square by 6. So guys, we are going to use this like tricky ideas a lot. Trust me, a lot. We are going to find the moment of inertia of different bodies in different ways. But that really depends on the examiner. If he really wants to give a lot of problems just to find moment of inertia, like I can give you a problem saying like this, something like this. Watch this thing. Yeah, I have two spheres. I need black. I have two spheres and I want the moment of inertia about this axis. So we already know this value. How much was that? Mr square by how much about this axis? It is 2 by 5 mr square plus md square, which is nothing but 7 by 5 mr square. For one sphere, you have two spheres, you simply multiply it by 2. So for two spheres like this, about an axis passing through the middle, if the spheres are rotating about the axis like this, if the spheres are rotating about the axis like this, all you have to do is simply take the moment of inertia 7 by 5 r square into 2 for two spheres. That's all. Okay. The problems can get complicated. It depends on your interest. So yeah, let's see if we come across some good problems. Moment of inertia is clearly not done. Like it depends on how many problems that you can do. You can practice it for 1 week and I can give you a body, yet you will fail to find the moment of inertia. It can go that far. So, but we don't need it for a mains level problems. This is good enough. But for advanced, yeah, you need to practice more for sure. Main level, this is more than good enough. Like you know the moment of inertia of almost a lot of bodies by now. Aditya, what is it?
Sir, can you find the moment of inertia along the diagonal of a square?
Yeah, beautiful doubt. So there is a question like that also. I have a square. I know these two values as ma square by 12 and ma square by 12. Let's just say Aditya is asking the value about diagonals. The best part about this is the diagonals are also perpendicular to each other. Let us just call it as ID1 and ID2. They are perpendicular to each other. So I can happily write ID1 plus ID2 is also equals to that IZ axis.
Oh,
We already know this value as ma square by 6 and these two are equal. So 2 ID1. So what are you getting the value as? ID1 and ID2 is
ma
also
square by 12.
ma square by 12 and ma square by 12 only. And it's not just that. Any axis, you take any axis in a squarish plate. You take any axis, a moment of inertia is basically ma square by 12. You will slowly realize these things. Like you will slowly by tonight and in the middle of sleep, you might, some idea might strike randomly that, okay, this is also there, this is also there. Be careful when you do this though. When you're doing for a rectangular plate, I need you to be really careful.
You need that breadth thing also there, sir.
What?
This time we will have two lengths.
Exactly. So for a rectangular plate, you have to be careful. You cannot do any silly things here. You have to stick to a point saying this is ml square by 12. This is mb square by 12. So if you want z axis, you have to shut up and write ml square by 12 plus mb square by 12. That is the only thing that you can do.
Yes, sir.
Okay, Aditya?
Yes, sir.
Yeah.
All cleared.
Yeah, so I've discussed a lot of bodies today. Yeah, I think we are good enough about moment of inertia discussions. Today, you're going to solve all these problems. Like somebody gives you a problem saying, find the moment of inertia of a sphere. Like find the moment of inertia of a sphere about this axis and find the radius of gyration also. We've already done this thing, 7 by 5 mr square. And I want the radius of gyration. I equate it to mk square. K comes as root over 7 by 5 r. That's it. For now, mathematically, what's the idea? What's the use of like mathematically looking at the radius of gyration? This is the value. That's all. But the real purpose of radius of gyration will be discussed maybe in the topic of rolling. You will get a much clearer idea what exactly is radius of gyration. So we'll do that there. Okay, for now, just try to understand the radius of gyration is this much, like this is it, that's all. Okay, now once we are partially clear about moment of inertia, now remember where we started about moment of inertia in the first place. We started here, torque equals to I alpha. This is what we were discussing. And we took a small detour into the moment of inertia, and we took us almost 2 days to discuss just the moment of inertia part. Let us just come back to this equation. Everyone knows how to find torque. Everyone knows how to find the torque. Everyone knows how to write the moment of inertia also. You'll get to see how easy the problems are. Now people will ask simply to ask you to find alpha value. That's all. Let me just give you a question, a very simple question. Let's just go through this thing. There is a disk, a very simple question I'm starting, fixed about this axis, so it can rotate about this axis. Sir, today I will try triangular lamina. Aditya is saying he wants to try triangular lamina also. Yeah, there are questions where they ask the moment of inertia for triangular lamina also. Yes, there are questions. You can try and send it to me. If I'm free, I'll take a look at it. Okay. Now let's come back to this problem. There is a disk of mass m, radius r. Everything will be mentioned. A force like this. I mean, I hope you're clearing. The force is in the plane, is acting on the disk. What is alpha that is created? Can somebody immediately do some calculation and tell me the answer? I'll discuss it anyway, but if you can do that, I'll be glad, really glad. The force is applied here, so it turns the disk. So what is alpha? How much is alpha? Everyone knows how to write the torque. The radius is definitely r, obviously. The radius is r. Everyone knows how to write the torque. Everyone knows how to write the moment of inertia. So what is alpha? Ganesh gave me an answer saying 2m by mr. What is that, Ganesh? No. Your fr equals to mr square by 2. 2f by mr. Ganesh is saying answer is 2f by mr. Let's just see. Anyone else has any answer to this? It's a very simple one. Because of this force into perpendicular distance, F into R is a torque equals to I alpha. I is nothing but about a disk. For a disk, it is nothing but mr square by 2 into alpha. Mr square by 2 into alpha. So R cancels. Alpha equals to 2f by mr. 2f by mr. Okay. A lot of people send me the answer. That's a good thing. 2f by mr is the angular acceleration that you just created. That's all. I can change the body, like I can change it to a sphere and somebody put a force on it. How much is the angular acceleration? F into r equals to, you simply put that thing value, whatever the value that is there, and find the value. That's all. So you will get to see a lot of problems like this, like basic friction. Like they give you a problem saying a sphere is rotating. It came into contact with a rough surface. It came into contact with a rough surface, and the friction slowed it down. So this friction is actually trying to stop the sphere. So I write it as minus friction into minus F into R equals to I alpha. So this alpha will be a negative value. We'll get a minus FR by I is the angular retardation of the sphere. Like once you get the angular retardation, again they give you a kinematics problem saying after how much time will it come to rest. Initial angular velocity will be given as omega naught. What is the final angular velocity? Oh, whoa, I didn't do anything, I'm sorry. Yeah, initial angular velocity will be given as omega naught. Final angular velocity is 0. So you'll have to do these problems like, omega final equals to omega initial plus alpha t. V equals to u plus at. Omega initial is given as omega naught. Omega final is given as 0. Alpha, we just found it as minus fr by I into t. From this, you can find the time t. That's all. These are the kind of problems that you're going to see a lot. Okay, so we'll let me show you those problems also in HC Verma. I hope you've all done this page already. Look at this page. Look at these questions. Guys, 21, question number 21, leave it for now. You won't understand it right now. Question number 21 can be left out. You can do the moment of inertia problems. Obviously, I asked them to leave them out that day. You can do the moment of inertia problems. So coming to 22, 23, 24, 25, a flywheel is nothing but a disk. A flywheel of moment of inertia is given. So they give you some silly problems on this page and this page also. Give them a try. It's all about basic writing torque, angular acceleration, and finding what is the amount of time it is rotating, what is the amount of deceleration and all. So it's a basic problem again. From this point onwards, the problems get a little bit difficult. From problem number 31, 32, 33, 34, all these problems come under a separate section. Today is Thursday, right? Yeah, we have Friday also. Like tomorrow, I'm going to discuss the problems. Like I'll just give you a glimpse of it. I'll just give you a glimpse of it. The kind of problems that you're going to face here. This is a basic pulley problem. We've all seen this kind of a pulley problems already. But the thing here is, these two used to have mass. In this case, he also gives a mass to this also. Remember in the topic of Newton laws, we always used to say things like the pulley is massless, the pulley is massless, the pulley is massless. Here, the pulley is no more massless. The pulley has mass. Now, so pulley has mass, it has R. So if the bodies are accelerating, the pulley is accelerating angularly. The pulley is accelerating, which means the tensions, if only the tensions on both the sides are equal, both the torques will be balanced. The pulley is not accelerated. Here you have to consider this as T1 and T2. The tensions are not anymore equal. The pulley has mass, the pulley has inertia, the pulley is accelerating. I will discuss these problems tomorrow, but there is an additional idea here. Like we will have to handle this thing. But this also gets very simple. Like in the first one or two problems seem difficult initially, but once you catch the point, all the problems get really silly. So we will do that tomorrow. So whatever I teach by tomorrow will be in the exam syllabus. All right. Before I end the topic, is there anything that is related to today's class that you have any doubts? Just related to today's topic, just related to today's. If there is anything, please let me know. If it is not related, please don't ask. Let me at least stop the video. Let's just meet in the video next class. Okay.